Hello learners, in this video we're going to be going through Edexcel Separate Science Foundation Physics Paper 1, the paper that we've written for 2024. So what you can do is pause after each question comes up, play the video, and then we can go through the answers together.
So this question is about radiation, and we're told that the sentences below describe different types of ionizing radiation. Here we need to fill in the sentences using the words in the box. So this is a great test of our knowledge, and it could even form your revision notes here, okay? Let's remind ourselves of what each of these are. You should remember that alpha radiation are helium nuclei. Now, a helium nucleus is composed of 2 protons and 2 neutrons. So filling in the sentences to start, we've got alpha particles are helium nuclei, and they are composed of 2 protons and 2 neutrons. The next chunk of sentences is about beta particles. We should know that beta particles are fast-moving electrons. And we should also know that gamma rays are electromagnetic waves. We've also learnt about them in the electromagnetic radiation, the electromagnetic spectrum topic. So that's what we fill in here. Beta particles are fast-moving electrons and gamma rays are electromagnetic waves. So now, out of these 3 types of ionizing radiation, we need to state which is the most ionizing and which is the most penetrating. Now, alpha is the most ionizing. Think about it, it's the physically biggest of all of these. So that means when it bashes into other atoms, it's far more likely to ionize them than the essentially invisible gamma. And so for that reason, gamma is the most penetrating. They sort of feed into each other really. Because it's not interacting with as many particles as it moves through a substance, it can penetrate further. So the final 2 sentences, out of these 3 types of ionizing radiation, alpha is the most ionizing and gamma is the most penetrating. Now, if you didn't know these facts, then please stop the video now and just write them down and get learning them, because gosh, these are such important facts that will get you so many easy marks in the exam. Complete the table by identifying whether the radiation is alpha, beta, or gamma. Well, looking at this first row here, we're asked which radiation is stopped by paper, aluminium foil, and lead. Now that is alpha radiation. Let me remind you of the experiment where all these are coming from. So we should be familiar with an experiment where we lay out a sheet of paper, then we lay out a really thin sheet of aluminium foil, and then also a good chunk of lead. And what we'll do is we take a radioactive source of either alpha, beta, or gamma, and we can detect the presence of that radiation behind each of these barriers, so the paper, the foil, and the lead. Now with alpha, what we notice is that all of it gets absorbed at the first step at that paper. None will be detected anywhere beyond that paper. So then if we think about beta radiation, that beta will make it through the paper, however it will get stopped by the foil. So looking at the 3rd row, beta gets stopped by aluminium foil, but not paper. Great. Gamma, on the other hand, will make it through the paper, it will make it through the foil, but it will still get stopped by the lead. So gamma goes in the middle. Next up, we're asked to identify a method that can be used to detect the presence of radioactive substances. Like I mentioned with this experiment that we see here, we would need to use some sort of detector of the radiation to determine its presence. Obviously, that's just one example of a use of this method to detect their presence. But we need to know what we're using, okay? So there's a couple of options you can give here to get your marks. The first example, and probably the one you've heard about the most, is the use of a Geiger-Müller counter or a Geiger-Müller tube. Or you might have heard it as just a Geiger counter. Any permutation of those will get you the mark. However, another option that you may have heard of and you may give is photographic film. Think about X-rays. Photographic film changes colour in the presence of radiation. So that is another option here that we could give to detect the presence of radioactive substances. If you don't know that, get learning it. Redshift is a phenomenon which supports the idea of the Big Bang Theory. Here we're asked to complete the sentences to describe the Big Bang Theory and to use the words in the box to help you. So here we're told that the Big Bang Theory is the theory that the universe began from a very something region that was extremely something and something, okay? So looking at the words that we have here, we need a description for this region. So the answer to this is that the Big Bang Theory is the theory that the universe began from a very small region that was extremely hot and dense. And by dense, it means that there was lots and lots of matter squeezed together into this very small region. And it happened to be very, very hot. So if you aren't familiar with this statement, then this is a perfect statement to turn into some notes because it's got all of those key facts in it that you need to learn. Here we're asked to tick 2 boxes that explain how redshift provides evidence for the Big Bang Theory. So this is a really important fact that we need to know. And here we need to tick 2 of these boxes. So starting off here, there is an observed decrease in the wavelength of light from distant galaxies. We should know that this is incorrect. And that's because of this statement of there being an observed decrease in the wavelength. That isn't the case. What we actually see is an observed increase in the wavelength of light from distant galaxies. For that reason, this second box is the one that we need to tick. The next few points are talking about how big that observed change in wavelength is. And if we compare the next 2 points, the nearer the galaxies are, the bigger the observed change in wavelengths. Again, isn't correct. Actually, the further away the galaxies are, the bigger that observed change in wavelength. So for that reason, this 4th box is the other box that gives us our correct answer. And so those are our explanations as to how redshift provides evidence for the Big Bang Theory. We need to know those 2 statements. We need to know that 1, the fact that there's an observed increase in the wavelength of light from distant galaxies. And secondly, the fact that the further away those galaxies are, the bigger the observed change in wavelength. And again, if you don't know those 2 facts, then please do make a note of them and get learning them. 2 light spectrums from distant supernovas are shown below. So here we've got supernova 1 and supernova 2, and you can see that this arrow shows an increasing wavelength. We're asked to identify which of the 2 supernovas is the furthest from the Earth and to give a reason for our answer. So what we need to notice here is in supernova 2, it's shifted towards the increased wavelength side. Now this means that the light from supernova B has experienced more redshift, and we can see that because the light from it has been shifted to a longer wavelength when compared to supernova 1. So to get our marks here, first we're going to state that supernova 2 is our answer, and our explanation for this is that the light has been redshifted, so it must be moving away faster. And that is our explanation as to how we know that supernova 2 must be the one furthest from the Earth. The Big Bang Theory produced hydrogen and helium. Since then, all other elements have been produced in nuclear fusion reactions in stars and supernova. Elements heavier than iron are formed during supernova explosions. The table below shows the stages in the life cycle of a star leading up to the formation of a supernova. We need to put these stages in the correct order by putting the letters in the correct spaces. So looking at these spaces here, I can see that it all ends with B, and B is when that supernova gets formed. So we need to think, well, what's going to be the very first step here? we need to know that the first step is that dust and gas in space are brought together to form a nebula. So I'm going to start off by putting E in my first position. So after that happens, and after we get this nebula, what's going to happen is gravity will pull together that nebula to form a protostar. So our second step here is going to be A. Okay, so we're doing great here. We've got our protostar. So the next step that happens is eventually we're going to form a main sequence star. And the sun, our sun, is currently a main sequence star. That's where it will spend the majority of its life. So we've got C now, a main sequence star forms. Obviously now we can see that the next option will be D, it's all that we have left. But yes, what happens when we do have this very large star is it becomes a main sequence star, but eventually it will expand to form a red supergiant. So that is our next step here. It becomes a red supergiant before eventually it becomes this supernova. So this is perfect again for making some nice, simple, straightforward notes. You could take these letters, but instead write the statements in a nice flowchart with these 5 different steps, and you can get memorising them in order. Or you could put them on a piece of paper, you can cut it up and see if you can place them in the correct order. There's lots of different techniques you can use to get memorising these. All that matters is that you know it. This question is about the motion of a train between 2 stations. Identify which of the following statements about speed and velocity is correct. Now looking at these options, I can see that the first and second one is talking about vectors versus scalars. So I think it's worthwhile we just talk about quickly what the difference is between a vector and a scalar. So a scalar is a quantity, only has magnitude. So it doesn't have any direction to it. Whereas a vector has both magnitude and direction. And what that means is it matters if you're going left or right or up and down. It's not just a case of, oh, I've got a speed of 5 meters per second. I mean, that will still be its velocity, but the velocity will be, I have a velocity of 5 meters per second to the left or to the right. Anything where you can represent it with an arrow. So having a look at this now, I should know that velocity is the vector of them both. And the great thing is about speed versus velocity. Speed begins with an S, it's a scalar, and velocity begins with a V, is a vector. So actually those two are kind of gifts to you really. They're the perfect examples to learn if you need to have one example in your arsenal for when the exams come up. So actually, without looking at the others, I can see that velocity is a vector is my correct answer, so I tick that 4th box. If we look at the others though, just to explain it, speed is always the same as velocity. That's not true because although the number part will be the same, it could be negative if you had velocity, for instance, if you were going backwards. Whereas if you were just looking at the speed, you don't care that you're going backwards, it would just be the number. Whereas the third point, velocity is measured in meters per second squared. No, velocity is measured in meters per second, no squared. It's acceleration that is measured in meters per second squared. So there we have it, velocity is a vector. Now we're asked to draw lines to identify whether the measurements are vector or scalar quantities. So these are just bits that we need to have memorised really, okay? So we need to know that distance is an example of a scalar. So distance just tells us how far we've gone, but it doesn't tell us in what direction. Displacement, on the other hand, is the vector version of distance because it does tell us if we went backwards, forwards, left, right, east, west, north, south. And acceleration is also a vector. And that's because you can accelerate and you can decelerate. You could go faster or you can be slowing down. So those are our answers to this question. If you don't know them, then make a note of all those facts and get memorising them, because they should all be easy marks in the exam. So now we're told that train X was travelling between two stations, station E and station B. Train X was stationary at station A. It then increased its speed to 50 metres per second over the next 40 seconds. So then the train continued its journey at a constant velocity for 1.5 minutes before decelerating for 30 seconds until it stopped at station B. So here we're asked to assume the train had constant acceleration and deceleration, and we're asked to complete the velocity time graph. So the first thing to look at is the fact that once it gets to this 50 metres per second, it has a constant velocity for 1.5 minutes. Now, if you look here at the x-axis, it's in seconds. So we need to know that 1.5 minutes is equal to 90 seconds. If you don't know that straight away, then you can just multiply it through by 60 in your calculator and you'd get 90 seconds. So as we left off at 40 seconds, if we add 90 to that 40, we know that we're going to stay at a constant velocity until we reach 130 seconds. So there we have it. So then we're told before decelerating for 30 seconds until it stopped at station B. So it's going to come to a stop, so it's going to end with a velocity of 0 and it's decelerating for 30 seconds. So at the minute we are at 130 seconds, and if we're going to decelerate for 30 more seconds, we're going to come to a stop at 160 seconds. So that means we're going to do a straight line, use a ruler and a pencil with this question in the exam, a straight line down to 160. And so there we have it, that is our completed velocity time graph. The line between t equals 0 seconds and t equals 40 seconds has a constant gradient. Explain what this constant gradient indicates about the motion of the train between t equals 0 seconds and t equals 40 seconds. So let's have a think, one at a time, of what these would all look like on a velocity time graph. So this first point here, the train is travelling at a constant velocity. That would just be a horizontal line, and that isn't what it looks like, so it can't be that. So the second point, the train speed is decreasing. That means that over time velocity must get less. And again, it didn't look like that. However, if the train's velocity was increasing at a constant rate, you would get this straight line, and so that is correct. But let's look at this last point as well. The train is stationary. That would just be another horizontal line, but this time at 0. Okay, so next up we're asked to calculate the acceleration of the train in the first 40 seconds. So let us remind ourselves then of what the graph looks like, because we're going to need to use that to calculate this. So there's two ways we could do this. The way that I would recommend that you do this is by using the gradient. We should recognise that the acceleration of a velocity time graph is found by calculating the gradient of the line. So before we do anything, let us just remind ourselves of the equation for the gradient. This comes up in all your sciences and maths. We need to know that gradient is equal to the change in y over the change in x. Or we might have learnt it as the rise over run. But here what I'll do is I'm going to change this into a little bit of a triangle here. Okay, so we've got 50 and 0. I can see that the change in y will be 50 minus 0. Then on the x-axis, I can see the change is 40 minus 0. So putting that into the calculator, I get a gradient and therefore an acceleration of 1.25 metres per second squared. As the train left station B from rest, it accelerated at 4.5 metres per second until it reached a velocity of 60 metres per second. Calculate the distance travelled by the train. So to do this, let's just think about what quantities we know. So here we've got initial velocity is 0 metres per second because it started from rest. The acceleration we're told is 4.5 metres per second squared. And we're told that it ends up, so it has a final velocity of 60 metres per second. And of course, we need to get the distance travelled by this train, so that there is our question mark. So looking at this, we should recognise the correct equation to use, okay? So the formula we must use states that the final velocity squared minus the initial velocity squared is equal to 2 times the acceleration times by the distance. So you can see me writing it here. So of course we need to find the distance and we know the other quantities. So what I would do here is just substitute those values in. So that leaves me then with 60 squared for the final velocity squared minus 0 squared. And then that's going to be equal to 2 times the acceleration, which is 4.5, times by the distance, which is of course our unknown. So if I simplify this now, and if I do 60 squared minus 0 squared in my calculator, I get 3,600. 2 times 4.5 times distance then becomes just 9 times distance. And rearranging this to get the distance on its own, we need to divide through by that factor of 9. So we're going to do 3,600 divided by 9, which gives us 400 metres. In this question, it was assumed that the acceleration of train X was constant. In reality, the train's acceleration decreases as the velocity of the train increases. Here we're asked to complete the sentences to explain why. Okay, so here we're told as the train's velocity increases, air resistance, and we should know that as we go faster, the air is hitting us more rapidly, and therefore air resistance increases. Now the effect of this is going to decrease the resultant force on the train. Of course, it's got that thrust pushing it forwards, but now it's got this air resistance counteracting that and making the overall force on the train less. So now it says force is proportional to acceleration. So because that resultant force has decreased, the acceleration will do the same because it's proportional, and it will also decrease. An investigation into the effect of tiredness on reaction time was carried out. 5 men were asked to complete the ruler drop test after 8 hours sleep. This was repeated after 4 hours sleep and 2 hours sleep. Here we can see a big table of all of our results, and we're asked to describe the trend in the results. Now, whenever we get a describe question like this with data, I always think we just need to say what we see. And I would always start with the general trend, and then for future marks, be more specific. So if I look at this, I can see that as the number of hours of sleep decreased, the reaction time increases. So that's the first thing that I can state. Now let's look into it in a bit more detail. If I compare, say, the 8 hours sleep to 4 hours and 4 hours to 2 hours, I can see that I get a bigger increase in reaction time going from 4 hours to 2 hours sleep than I do when I go from 8 hours to 4 hours. And if you want to, you can give some data here. But this is how I deal with these describe the trend questions. We want to say what we see, give one as the very general trend, and then for future marks, just look at the more specific changes and describe those. Okay, so now we're asked to identify the independent and dependent variable in this experiment. So for the independent variable, we need to think, well, what is it that I am changing? What is it that I am going to change from one experiment to the next? Okay, so what we need to do here is we need to remember that we're going to repeat this experiment for different amounts of sleep. So for that reason, the thing that I am changing as I do this experiment is going to be the number of hours sleep. Next up, we need the dependent variable. And what the dependent variable is the variable which will change because of what we changed previously. So as we change the number of hours sleep, what we will see happen is the reaction time change, and that's what we're measuring. So the independent variable is what I am going to change, and in this case, that is going to be the number of hours sleep. And the dependent variable is the thing that we're measuring, the thing that changes because of what I changed, and that in this case is the reaction time. Describe a suitable method for this experiment. Include in your answer how accuracy can be increased. Now, this is one of those classic 6-mark questions. And the important thing to remember with these is that we're not getting 6 marks for 6 points. Unfortunately not. What we instead need to do is to identify all of the steps that we need, put them in a nice logical order, and make sure that the method we give gives us a valid set of results. Now, in this question as well, you can see we also need to include how the accuracy can be increased. If any steps are missed out, then it can really have an impact on the level of our answer. The way that these are classified are level 3 answers, which get us 5 to 6 marks, when we've got this really full detailed logical method. Level 2, most of the steps of the method are there, but maybe they're not in a logical order, and maybe we wouldn't then get valid results. Whereas a level 1 answer, which will only get you 1 or 2 marks, only gives some of the steps and you wouldn't get any valid results. So we need to be very careful here to make sure that we don't just try and only give 6 points. It's not about 6 points, it's about a full answer, giving you the beginning, middle and the end of this method, and making sure that we explain, in this case, how accuracy can be increased. So let's get down to business then. Let's look at the method. So the first thing that we need in this method is going to be to ask the person to sit at a desk with their hand out. So once they've done that, you're now going to hold the ruler up to their hand, and you're going to make sure that you line up the 0 on the ruler with the person's thumb and forefinger. So that's an important step then. So now for the next step of our method. You're going to tell the person what they need to do. You're going to tell them that when the ruler gets released, they need to catch it as quickly as possible. So now we're going to drop the ruler, but very importantly, we're not going to tell the person when we're doing it. For your 5th point, we're going to measure the distance travelled by the ruler between the point it was dropped and the person caught it. Now this is where the maths comes in, and this is needed in this method to find this reaction time. We need to first calculate the final velocity of the ruler. And to do that, we're going to use the equation which is given in our datasheet, which states that the final velocity squared minus the initial velocity squared equals 2 times by the acceleration times by the distance travelled. And in this case, our acceleration, because it's falling under gravity, is going to be equal to either 10 or 9.8 meters per second squared, which is the acceleration due to gravity. Both of those options are perfectly acceptable. So now we can actually get on to calculating that reaction time. And to do that, we're going to use the fact that we know acceleration is equal to the change in velocity divided by time. Now, acceleration, we've already said, is going to be the acceleration due to gravity. And the change in velocity we can now find, because that's going to be the final velocity minus the initial velocity. Final velocity we would have just calculated, and the initial velocity was just 0, wasn't it? Because it was dropped from rest. We could, of course, rearrange that equation and say that time is equal to the change in velocity divided by the acceleration. So now we've got our full method there. Let's look at how we can increase the accuracy of our answer. So one of the things we can say that we should always say is we want to do repeats and find an average, or find the mean. And the other thing is to ensure that there's as few distractions as possible present. We want to know that any delays that are found in the reaction time is purely due to the amount of sleep that they had and not due to any other factor that might be present. Now, the method that we've given here is very thorough. Like I say, it's got a beginning, a middle and an end. We've shown some equations, and sometimes you might need to talk about graphs that might be plotted in other questions. And we've made sure that we've done exactly what the question wanted. We could see that the question wanted us to include in our answer ways in which we could increase the accuracy, and we have mentioned that as well. So this would be a 6-mark answer. Make sure you give it a good revise and you understand how it got full marks. Hinkley Point is a nuclear power station. The nuclear power station generates energy using the radioactive decay of uranium. Complete the sentences about radioactive decay. Okay, so we need to know that radioactive decay is a random process. This means that it is impossible to predict which nucleus will decay next. During radioactive decay, the unstable atomic nuclei give out radiation to become more stable. Activity is measured in becquerels and is the rate of decay of a source of unstable nuclei. Now, these sentences are really helpful because they summarise a lot of the facts that you need to know about radioactive decay. So if you weren't familiar with these facts, then I recommend that you make some notes on this right now. Don't wait until the video is finished, pause this now and make some notes or some flashcards so that you know exactly what it is that you need to learn for this exam. In 2020, 45 terawatt hours of UK energy was generated via nuclear energy. This is 15% of the total energy generation. Here we're asked to calculate the total energy generated in the UK in 2020. Well, if we know that 15% is equal to 45 terawatt hours, we can use that to work out what 100% is. Now, the way that I would do this is I would go down to 1% by dividing both sides by 15, and then I get 1% equals 3 terawatt hours. Once I know 1%, I can easily go up to 100%, and I do that simply by multiplying both sides here by 100. So then 3 times 100, I get 300 terawatt hours, and that is the total energy generated in the UK in 2020. So now we're told that the nuclear fission of 1 kilogram of uranium releases 8 times 10 to the 13 joules of energy. Here we're asked to calculate how many kilograms of uranium are required to provide 45 terawatt hours of UK energy. So the first thing I would do here is I would work out, well, how many joules is 45 terawatt hours? They've given us a little conversion here, and they tell us that 1 terawatt hour is 3.6 times 10 to the 15. So therefore 45 terawatt hours will be 45 times 3.6 times 10 to the 15. And that ends up giving us 1.62 times 10 to the 17 joules of energy. So we're told that 1 kilogram of uranium releases 8 times 10 to the 13 joules of energy. So to work out how many kilograms of uranium we need to take that 1.62 times 10 to the 17 and divide it by 8 times 10 to the 13. So that's going to tell us how many of these 1 kilograms we need. When I do that, I get 2,025 kilograms, and that is the number of kilograms of uranium required to provide 45 terawatt hours of UK energy. The graph below shows how a radioactive sample of uranium decays over time. The graph can be used to find the half-life of uranium. Here we're asked to identify the definition for half-life, and this is a definition that we need to know. We need to know that half-life is the time it takes for the number of nuclei of an isotope to halve. So we're going to tick that second box there. Now we're asked to use the graph to actually find the half-life of uranium. So we start with 100 grams, and we're looking for the time it takes for this mass, which equates to the number of nuclei, to halve. So we're going to go along at 50 grams, find where it hits the curve, and then we're going to read down. Make sure you use a pencil and make sure you use a ruler. Now I can see that that is 4.5. However, notice it's time in billions of years. So we're not just going to write down 4.5 or 4.5 years because that wouldn't get us our mark. We need to write down 4.5 billions of years. And this is a 2-mark question, so make sure that you do leave your lines on the graph to show how you worked out the half-life, because actually that's going to be your method marks for this question. So the lines, like you can see that I've drawn, are going to be something that your examiner is looking out for. Nuclear power stations such as Hinkley Point must take precautions to ensure their staff are safe. Here we need to describe 2 ways to minimise hazards caused by working with radioactive materials. And obviously this is a 2-marker, but there's so many things we can say. So I'm going to tell you a range of things and you can pick any 2 that you prefer. So the first thing we can say is we can wear protective clothing. Another thing we could do is wear face masks to prevent any inhalation of radioactive materials. Another thing we could do is limit exposure time. Make sure that people aren't spending too long, more long than they need to, in contact with these radioactive materials. Another thing we can do is if the people need to handle the radioactive materials, make sure that they're not using their fingers. Make sure that they use tongs. Another thing we could say is whenever we're not using these radioactive sources, make sure that they are shielded. So perhaps that could mean leaving them in lead-lined boxes. And finally, the last thing that we could say here is monitor the people's exposure. So we can get little things like detector badges, which is going to make it clear when people have spent too long or are approaching too long in this radioactive presence. Now, any 2 of those would get you your marks. So now we're told that research is constantly being carried out on the effects of radiation on humans. And here we're asked to explain why it's important that this research is shared. Now, this is not specific to this topic. This is universally true of any sharing of research in science. So the reason why it's important that this research is shared is so that this research can be checked by peer review. And what that means is that other scientists can check the work for its validity. So if you weren't familiar with the importance of sharing research, then make a note of it now. A bouncy ball of mass 0.05 kilograms is dropped from a height of 1.1 metres at a point A onto the floor at point B. The path it takes is shown below. Here we're asked to calculate the gravitational potential energy of the ball at point A and to use this equation, where gravitational potential energy equals mass times gravitational field strength times height. Now in this question I can see that the mass is 0.050, the gravitational field strength is told to us to be 9.8, and the height we're told is 1.1. So here to calculate gravitational potential energy, all we need to do is to take 0.050, that mass, times it by 9.8, the gravitational field strength, and times it by the height of 1.1, and we end up getting our energy. So that gives me 0.539 joules. And that is our answer to part A. Here we're asked to complete the sentences using the words in the box to help us. So let's remind ourselves of the scenario here, okay? So we have the ball at position A and it is falling down to the floor, which is position B. So here we're told to fill in this sentence. As the ball falls from A to B, the gravitational potential energy, and we need to realise here that it's going to decrease because the height of the ball is decreasing. And as the ball falls from A to B, the kinetic energy increases. Now what's happening here is as the gravitational potential energy decreases, it doesn't disappear, it's getting transferred to the kinetic energy. And that is why, as the gravitational potential energy gets smaller, the kinetic energy increases. And in fact, in a simple system like this, we can assume that all of that gravitational potential energy that it had at A will eventually get transferred to kinetic. And that really leads us to part C here. Here we need to state the kinetic energy at point B. And whenever a question says state and they're asking for a number, that means it should be quite obvious. We shouldn't need to calculate anything. The number should already be available to us. And what we need to understand here is that we calculated the gravitational potential energy at A, didn't we? We calculated it to be 0.539. And as it falls, this ball, as it falls towards B, all of that gravitational potential energy will get converted into kinetic. And therefore here, where they want us to state the kinetic energy at point B, the answer is simply 0.539. So see, we didn't need to do any calculations. I always think that's a bit of a hint in a question like this, that we've already got the answer, and maybe sort of have a look at what we've done earlier in the question or some information that's been given to us to see if that is actually our answer. Now we need to identify the equation that links kinetic energy, mass and velocity. So we should recognise that kinetic energy equals 1/2 times mass times velocity. So we're going to put a tick in that first box. Now in E, they ask us to calculate the velocity of the ball at E. Now they've helped us here by telling us the equation for kinetic energy. And the reason why that's so important is because that's what we're going to use to calculate the velocity. Now in the last part of the question, we said that the kinetic energy was equal to 0.539 joules. We were also told at an earlier part of the question that the mass was equal to 0.050 kilograms. So now we know kinetic energy and we know the mass, we can substitute them into this equation. So here we have 0.539 equals 1/2 times 0.050 times by the velocity squared. Now in this case, velocity is our unknown. So we need to rearrange this equation to get the velocity all on its own. I'm not going to rush that though, okay? First things first, I'm going to get velocity squared on its own. And the way that I'm going to do that is by dividing by that chunk that I've highlighted here. So I'm going to do 0.539 and I'm going to divide it by 1/2 times 0.050. Now, popping that into the calculator, I get that the velocity squared is equal to 21.56. Now finally, if I want the velocity on its own, I need to get rid of the squared, and the opposite of squaring is square rooting. So I'm going to square root 21.56, and that gives me 4.64 meters per second. And that is the velocity of the ball at point B. Now in this question, obviously we had to use the kinetic energy from an earlier part of the question. Now, if you couldn't do that part C, then potentially you're not able to do this part as well. And so my advice to that, to be honest, is if you didn't know, you didn't have a clue how to do part C and to state what the kinetic energy is, just write down any number, honestly. Because if you have any number that you can use, then you could substitute that into this question and you would still get your marks, okay? Maybe you would lose 1 mark, but everything else is the same. You've understood you need to substitute in kinetic energy and the mass. You can rearrange it. Never ever lose out on a mark just because you didn't work out something earlier that you need in this part. You can still show all of your method marks and therefore you're still getting closer to that grade that you need. When the ball rebounds, it doesn't reach its original height. The maximum height it reaches is point C. And so let's remind ourselves of that diagram. So you had the ball A, it fell down to the floor, which was B, and then it bounced back up. It never quite returned to its original height. So the reason why it didn't actually reach its original height is because some of the energy upon bouncing got dissipated to the surroundings. And that's often going to be in the form of heat energy. And so alternatively, you could say that some energy got dissipated as heat energy to the surroundings. But that is going to be our explanation. And that's true of many different examples. If you ever have an energy transfers question and they say, well, why didn't as much energy get transferred as we thought? Then it's generally going to be because some energy got dissipated to the surroundings. Commercial kitchens can make use of several types of electromagnetic waves to cook food and ensure safety. All electromagnetic waves are examples of transverse waves. And transverse waves look a bit like this, you might remember. Here we're asked to identify two other properties common to all electromagnetic waves, and we need to tick 2 boxes only. So we should know that they all travel in a vacuum, which means that they can travel in space basically. They don't need air or any particles to travel. And they all travel at the same speed in air. So when they are travelling through air, whichever electromagnetic wave you have, be it gamma or radio, it will still travel at the exact same speed. So the others are incorrect because the electromagnetic waves form a spectrum, and as you go along that spectrum, the frequencies and the wavelengths change. And it's not true that they can only travel in air. They can travel in many different media, including no media at all, just a vacuum. Microwave ovens can be used to cook and reheat food. Microwaves are electromagnetic waves. The electromagnetic spectrum is represented by the diagram below. And here we can see that it goes in order of increasing wavelength as you go from left, where we have Q, up to P. So here we're told that P are microwaves. And we're asked to identify the electromagnetic wave represented by the letter Q in the diagram. Now, to answer this, we really need to know the order of the electromagnetic spectrum. So I'm going to tell you a little mnemonic here that can help you to learn it. Okay, so I like the mnemonic that states that rabbits meet in very ultra expensive gardens. Okay, so that is our mnemonic, and the whole point of a mnemonic is it gets the order of things in the right places. So it's the first letter of each of these words. Well, expensive is a bit of a cheat, but it's the first letter of all of these words that will then give us the clue as to the order of different waves of the electromagnetic spectrum. So we've got the R, the M, the I, the B, the U, the X, and the G. And that tells us that we have radio waves, followed by microwaves, followed by infrared waves, and then visible light waves, UV for ultra, and X-ray for expensive, and gamma for gardens. Now, of course, you can come up with your own mnemonic, but all that matters is that we know the correct order of these parts of the electromagnetic spectrum. Now, obviously, you can do this in either order, can't we, okay? And in this diagram, that P is the M, it's the microwaves. So Q is the part on the other side, which is gamma. So therefore, Q are gamma rays. So now we're asked to identify one other type of electromagnetic wave that can be used to cook and reheat food. So we should be familiar with the fact that infrared radiation can also be used to cook. Infrared radiation is our standard heat energy. So any type of cooking which involves like this glowing heat, like a toaster or a grill or something, we are using infrared radiation. So next up, we're given a diagram which shows the microwaves emitted by a microwave oven. So here we're asked to select the correct value of the wavelength of this microwave. So we need to recognise that this diagram here actually shows 2 complete wavelengths. A wavelength could be from peak to peak or trough to trough, or it could just be one complete wave. So here I hope you can see from my diagram, actually this is 2 complete waves. So for that reason then, this 24 centimetre represents 2 wavelengths, which means that one wavelength would be half of this. So the answer to this would be 12 centimetres. However, they don't have 12 centimetres here. All of these options are in metres. So for that reason, we need to convert it to metres. We do that by dividing by 100, which gives us 0.12 metres. So that is our answer to part D. Next up, we're asked to calculate the frequency of the microwave in the diagram. And we're told that the speed of the microwave is 3 × 10⁸ metres per second. So now we need to give our answer in standard form as well, okay? So that's going to be an important part of our marks. Now to do this, we need the equation. Wave speed equals frequency times by wavelength. We can see here we're being asked to find the frequency. And we've been told the wave speed, we've been told that that's 3 × 10⁸. And we also know that the wavelength is 0.12 metres. We got that in the previous part of the question. So if we rearrange this to get frequency on its own, we need to divide through by the wavelength. So that gives us frequency is the speed divided by the wavelength. So that's 3 × 10⁸ divided by 0.12. And so that gives us 2.5 × 10⁸ Hertz. And that is our answer in standard form, and so we've got our marks. Ultraviolet light is also an electromagnetic wave. Here we're asked to complete the sentences to describe the differences between the properties of ultraviolet light and microwaves. And we're asked to use the words from the box to help you. So we should recognise that ultraviolet is going to be a shorter wavelength compared to microwaves. And to know this, we really just need to know the order of that spectrum that we mentioned earlier, and we need to understand that the gamma end has the shorter wavelength and microwaves have the longer wavelength. So here I'm going to say that ultraviolet has a shorter wavelength than microwaves. So wavelength and frequency are inversely proportional. When one of the two is bigger, the other one is smaller, and vice versa. So because we've got this shorter wavelength for microwaves, we're actually going to have a higher frequency, whereas the microwaves would have a lower frequency. So when we look at the sentence here, ultraviolet has, we can see the answer will be a higher frequency than microwaves. And now we've got ultraviolet has something energy than microwaves. Well, the one of the two that has the highest frequency has the highest energy. I always imagine my high frequency wave oscillating really quickly to get all these waves in. And it just feels higher energy too. Whereas when I've got this like slow, lumbering, low frequency microwave, it doesn't feel like something that's going to have very high energy. At the same time, the other way you can think of it is the more dangerous side of this electromagnetic spectrum. So the gammas, the X-rays, the ultraviolet, they are also the higher energy electromagnetic waves because it's that energy that can cause more damage. So here for this next part, we're also going to say that ultraviolet has a higher energy than those microwaves as well. So ultraviolet light can be used in commercial kitchens to kill bacteria. However, there are risks associated with using ultraviolet light. Here we're asked to tick one box to identify a harmful consequence to humans by ultraviolet light. So ultraviolet light is the light that comes from the sun that can cause us damage to our skin. So in the summer, when we're putting on our sun lotion, the reason for that is because the ultraviolet light can lead to skin damage and skin cancer. So the box that we want to tick here is that it can increase the risk of getting skin cancer. The time period of an ultraviolet wave is 2.9 × 10⁻16 seconds. Here we're asked to calculate the wavelength of this ultraviolet wave, and we're told the speed of ultraviolet light is equal to 3 × 10⁸ meters per second. So the equation that we need to use here states that the wave speed is equal to the distance travelled by the wave divided by the time that took. So in this particular question, we're talking about time period and wavelength. So in this case, that time period is the time that we're referring to. Now, a time period specifically refers to that time it takes for one exact wave to pass. And of course, if we then think about what a wavelength is, that is the distance essentially of one wave. So here then, when we're asked to calculate the wavelength, we can use this equation and rearrange it to find that distance. So at the moment it's distance divided by time. To get the distance on its own, we need to multiply through by that time. And so we get wavelength equals wave speed times by time. That's going to give us 3 times 10 to the 8 times by 2.9 times 10 to the minus 16. And so that is going to give us our wavelength. Putting that into the calculator, I end up getting 8.7 times 10 to the minus 8. And that there, in meters, is the wavelength of this ultraviolet wave. Local councils can reduce the speed limits outside schools from 30 miles per hour to 20 miles per hour. Reducing speed limits from 30 miles per hour to 20 miles per hour typically results in more than 20% fewer casualties. Decreasing the speed of cars in this way decreases the stopping distance. Here we're asked to identify the equation for the stopping distance. So this is a little fact that we do need to know. So if you don't already know it, make sure you get learning it. We need to know that stopping distance is the sum of the thinking distance, which is the distance that we travel between the moment that we see a hazard and we put our foot on the brake, and the braking distance, which is all about the quality of your car and the road, and that is the distance that you travel from the point you put your foot on the brake until you actually come to a stop. So stopping distance is found by adding these two together, which means that this one here is our answer. So now we're asked to identify which factors increase braking and thinking distance, and we need to draw 4 lines only here. So thinking distance is all about our reaction time, so we need to think what is going to make our reaction time get bigger. Now icy conditions won't do that. However, lack of sleep will. If we don't sleep and we're tired, then our reaction times and therefore our thinking distance will increase. Now having a worn tread on our tyres, it won't affect our reaction times. However, drinking coffee might do. It might speed up our reaction times. However, here, almost like a trick question, we're looking for factors that will increase the braking and the thinking distance. So that means it's going to take us longer to react, and coffee won't do that. In fact, we're often advised that if we're feeling a bit tired in a car and we're driving, that you should in fact take a stop, take a break, and get yourself a coffee, because it's going to counteract that reduced reaction time. So finally, we've got consumption of alcohol. Now, alcohol is a drug that is a depressant, and it does indeed slow down our reaction times. So therefore, our thinking distance would increase when we consume alcohol. Next up, let's think about the braking distance. Now, when we're in icy conditions, we're going to have less friction between our tyres and the road surface. Now, that reduced friction is going to increase our braking distance. Lack of sleep won't affect our braking distance. However, having a worn tread on our tyres will. So what a worn tread on our tyres will do is, again, it's going to reduce that friction between your tyres and the surface of the road, which means you're going to travel further and have a bigger braking distance before you actually come to a stop. Now, drinking coffee won't affect the braking distance, and neither will consumption of alcohol. So we've got our 4 options here and we've finished. Nuclear fission and nuclear fusion are 2 possible methods of generating energy that does not involve the use of fossil fuels. Almost 20% of all electricity in the UK is generated using nuclear fission. Nuclear fission takes place in nuclear reactors like the one below. Here we're asked to complete the sentences below to explain how nuclear fission generates electricity. So we've got a load of words in the box to help us out. So we need to know that nuclear fission releases thermal energy, so heat energy. And we need to know that this energy causes the water to boil and to turn to steam. and that steam will rise up as it's a gas, and it's going to turn a turbine, which then will turn a generator. And it's that generator that generates electricity. So here we have a few sentences that are perfect model answers for this explanation as to how nuclear fission generates electricity. So if you weren't familiar with these facts, then I would recommend you pause this video right now, get out a flashcard and write this down and go away and get learning it. And then you're guaranteed to get it right in the exam. Control rods are present in nuclear reactors to absorb neutrons. In the event of an emergency, the control rods can be fully inserted into the reactor to stop the process of nuclear fission. Here we're asked to use our knowledge of the process of nuclear fission to explain how this would stop the chain reaction. So in order to answer this, we need to have a think about what this chain reaction is, okay? We need to know that fission releases neutrons. So every time we have a nuclear fission reaction take place, more neutrons get released. And these neutrons will then go on and be absorbed by more uranium atoms. And therefore, we're going to cause more fission, and this chain reaction is going to perpetuate. So if we put these boron rods, these control rods, all the way into the reactor, then we're now going to absorb all of these neutrons. And therefore, there's going to be no neutrons left anymore to go on and cause this chain reaction. And therefore, these control rods have actually stopped this process of fission. So in this question, where we're asked to use our knowledge to explain how this would stop the chain reaction, we need to write down two of these points. So we could firstly say that fission releases neutrons. That could be one mark. We could state that these neutrons are absorbed by more uranium and cause more fission. And then we could also say that neutrons all get absorbed by these control rods when they get fully inserted, and therefore this would stop the fission. So writing any two of those key points would get you your marks. Here we're told uranium-235 and plutonium-239 are the most used nuclear fuels for nuclear fission. Here we're asked to use the numbers from the box to complete the equation for nuclear fission. So this is just algebra basically, which I hope doesn't scare you. It's really simple algebra. What we need to do is to consider all of these top numbers, and you can see I've highlighted them here. So we've got 235 plus 1, and that needs to be equal to all of those numbers on the top of the product side. So that's going to be 144, and then plus this mystery number that we need to find, and then plus 3 times 1, because we have 3 of these neutrons. So now you can see we've got a nice little equation here. We can simplify what we have on the left. That gives us 236. And over on the right, 144 plus 3 times 1 gives us 147, and then plus this mystery number. So if we rearrange this by doing 236 minus 147, we find that the number we needed to get is 89. So we can fill that in here. So now we want to do exactly the same process on the bottom instead now. So here we're going to have 92 plus 0 this time equals this blank that we need to find, plus 36 plus 3 times 0. So 92 plus 0 is just 92, and 36 plus 3 times 0 is just 36. So if we rearrange this by doing 92 minus 36, we find that our mystery number is 56. And so there we have fully completed our equation, and we've got all of those important numbers that we needed. Although both nuclear fission and nuclear fusion generate energy, only nuclear fission is currently used in reactors to generate electricity. However, in 2022, scientists made a huge breakthrough in their work towards finding a way to use nuclear fusion in reactors. For the first time in over 70 years of research, they were able to generate more energy from a nuclear fusion reaction than was required to initiate it. So here now we're asked to complete the sentences to compare the processes of nuclear fission and nuclear fusion. And it's really important that we know these differences. So here, nuclear something is the splitting of a heavy nucleus into a lighter nucleus. So this here is fission. So we need to know nuclear fission is all about splitting heavier nuclei into lighter ones. So therefore we can almost just guess what the other one is. It's going to be fusion, isn't it? But let's look at the definition. Nuclear fusion is the joining of two lighter nuclei to form a heavier nucleus. And if you just think of the word fusion, we've got these light nuclei fusing together to form a heavier nucleus. I always think that makes sense to me, just the meaning of that word. So those are our two definitions essentially of what nuclear fission is and nuclear fusion in really simple terms. So if you weren't familiar with that, then again, pause this video, get out your flashcards and get making those notes now, because then you're not going to waste any time and you're going to be able to get these right in your exam. Identify the reason why nuclear fusion requires so much energy to initiate. So this is a really important question. The answer is that we need to overcome the repulsion between nuclei. Let's think about that for a minute. Nuclei are positively charged, and therefore these positively charged nuclei are going to naturally want to repel each other because they have the same charge. And remember, like charges repel. So for that reason, we need to overcome that repulsion. We need to put in additional energy to force them together. And that is why we need so much energy to initiate nuclear fusion, because we need to join together these lighter nuclei to form a heavier nucleus.
Well done, lovelies. I'm really, really proud of you for making it all the way to the end of this video.